So there are two notes pages. The first one looks like this, phase change notes. That one's going to go on page 41, and then there's also going to be this one that says temperature scales. It's a half sheet, so temperature scales, and it'll give you some practice doing some energy conversions as well. So let's just jump in. States of matter, remember, solid is tightly packed. They're just vibrating in place. Liquids, there's a lot of particles in a small amount of space, but there's enough room where they can move around, and of course gases are very spread out, so they can move much quicker. The big idea here is when you're adding heat energy, we can cause solids to go to liquids and liquids to go to gas, and when you're removing heat energy, you can cause a gas to go to a liquid and a liquid to go to a solid, and we'll talk about those. So what is a phase change? It's just a change in the state of matter of a substance. Remember, states of matter are solid, liquid, gas. There is also plasma, but it's not a state of matter that we really discuss a whole lot in 8th grade science, and it's also not a state of matter that we talk about with phase changes, so we'll just kind of keep that on the back burner. This is just a basic graph that shows you as temperature is increasing and we're adding heat energy over time, that we can see that solids turn to liquids, turn to gases. If we're removing the heat energy, gases can turn to liquids and can turn to solids, and we'll look at that a little bit more specifically here. So first of all, if we're adding energy or we're adding heat, you're going to see that a substance causes the molecules to start moving faster, and this causes the temperature to increase. When heat energy is added to a solid, it's going to melt and become a liquid. And when heat energy is added to a liquid, it will boil or vaporize and become a gas. So a couple key words there that you need to remember, obviously the melting and boiling. Melting and boiling happen at a specific temperature for a specific substance. So we know that, for example, water boils at 100 degrees Celsius, but that wouldn't be the same case for what temperature, let's say, rubbing alcohol would boil at. That would be a different temperature. So it's a unique, what we call characteristic property. If you remove heat energy, the opposite happens. Obviously, the molecules are going to start to slow down and the temperature is going to decrease. When heat energy is removed from a gas, it's going to condense and become a liquid, so that's the phase change. You guys are familiar with condensation from cloud formation. The water vapor in the air cools and turns back into liquid as clouds are formed. And if you continue to remove heat energy from a liquid, it will freeze and become a solid. You guys watched that happen with the lauric acid in the lab we did last week. Again, freezing point is unique to the substance. So lauric acid froze at, I don't exactly remember, I think about 45, 46 degrees Celsius. But we know that water freezes at 0 degrees Celsius. Rubbing alcohol, it's going to be a negative temperature. It's going to be below the freezing point of water. So each substance should have its own unique freezing point. So what's actually happening during an actual phase change? So when the solid is melting or the liquid is freezing or the liquid is boiling, etc. So when heat energy is added to a substance, the temperature increases until it reaches a phase change. So think about how you saw when you had just liquid water and the temperature just kept jumping every minute that you're recording. It's 11 degrees, now it's 17 degrees, now it's 28 degrees, and so on. But all of a sudden it started to kind of stay still at the same temperature for a few degrees. So during a phase change, the temperature stays the same because now all that heat that's still being pumped in there by the hot plate or whatever the heat source is being used to break those bonds, the attractions between the molecules. So the temperature actually doesn't change, and we notice that on a graph we would see a flat line, or some people call it a plateau, indicating that, hey, the temperature is not changing because the phase change is occurring right now. So all that energy that's being pumped in, or all that energy that's being removed, is being used to actually form a new state of matter. You guys probably saw that with the lauric acid. The lauric acid, you guys were like, hey, it's still 47 degrees. Hey, it's 47 degrees again. Why is it staying at about the same temperature? Well, because all of a sudden that phase change was happening. So when a phase change happens, we tend to see the same temperature until the phase change is complete. If I had you recording the temperature temperature of the lauric acid for a whole hour, we would have seen it start, once it was fully solid, it would have gotten cooler and cooler until it reached the same temperature as the air, which was probably 20 degrees Celsius. So you do need to know these things. These three things, the boiling point, melting point, and freezing point, are unique for a substance, like I was saying before. So boiling point, temperature which a liquid turns into a gas. Melting and freezing point tend to be the same temperature. It just depends, am I adding energy or taking it away? Because if I have liquid water and I expose it to 0 degrees Celsius, it's going to probably freeze into a solid. At the same sense, if I have solid ice cubes and I expose it to about 0 degrees Celsius, it's going to start to melt. So at 0 degrees Celsius, we can see liquid and solid water at the same time. That's like an ice water bath. It should be right around 0 degrees Celsius. So if I have ice at 0 degrees Celsius and I'm heating it up, it's going to turn to liquid. Whereas if I have liquid water and I put it in my freezer where it's below the freezing point, and so heat energy is being removed, then it's going to freeze. So we would say the freezing point and melting point of water are both 0 degrees Celsius. This just shows you a basic phase change diagram. You're going to have to learn how to read and interpret and even draw one. So you usually see two plateaus for all the phase changes. Here in this section labeled A, it's just a solid. Now it could be a solid and a liquid at the same time. That was like that ice water. So it's in the process of either melting because I'm heating it up or freezing because I'm cooling it down. So let's go with the lab that we did on the hot plates. I started with ice. It started to turn to liquid right away. Some melting was occurring. As soon as it was all liquid, that would be letter C here, we saw a pretty quick and rapid increase over time as the temperature went up and up and up and up and up. And then all of a sudden we hit about 95, 96 degrees, and we were starting to jump into that. We're getting real close to 100 degrees Celsius where water can vaporize or boil. And so that occurred, and if we were able to watch it for a long time again, we were watching it for like 45 minutes, we would have seen that this about 100 degrees Celsius, give or take a degree on those thermometers, would have stayed at the same temperature for several minutes until it was all gas. And then if we were collecting this like in a closed chamber and could trap the gas and just not release it to the room, the gas would start to get warmer and warmer. So this is a basic phase change. Now you guys were looking at the lauric acid right here. It was all liquid when I gave it to you. So it started about 70, 80 degrees Celsius. It rapidly dropped down, and then the freezing point was about 47 degrees Celsius, give or take a few degrees. And then you saw it stay at that temperature for a little while because, again, it was freezing, so there was some liquid in there, some solid. Once all the solid had been reached, it could continue to drop in temperature until it reached equilibrium with the room. One of the things you guys researched a little bit about, and one of the activities was the different technologies that we use for heat transfer. Heat engines, that's a device that converts thermal energy into mechanical energy, so like steam engines. But there's really a lot of different things that are starting to use heat engines more. In fact, even our cars are considered heat engines because they do combustion. Again, this is using heat through usually steam or some fluid, so it would be a convection. Heat pumps and refrigerators, they just work in opposite directions. So a lot of new houses now have heat pumps, and what it does is it just removes the heat from the air outside and blows it into the house. And so this actually does use a conductor. It uses metal pipes and tubings to actually cause some of the air to come in contact and heat up. But it's also the principle of convection because there is an exchange of heat through the fluids. But we can run this in reverse as an air conditioner. It sucks all the heat out of the house and blows it outside. And so either way, it's removing heat. The same thing happens in your refrigerator. Believe it or not, your refrigerator is not making cold air. It's just sucking the heat out. So it cycles the air through these metal pipes, and it attracts and takes all the heat and blows it outside of the refrigerator. If you ever feel the bottom of your refrigerator or behind your refrigerator, it's probably warm when it's running because it's sucking heat out. And when it removes some of that heat, the resulting temperature drops. Thermostats, this is a little bit easier to understand. There's old-fashioned thermostats used usually like metal rings, or it used like metal coils, or it used mercury. The metal coils, as they heated up, would expand, and when they expanded to a certain point, it would flip a switch on to turn the air conditioner on. And when it got cold, the metal coils would constrict and get smaller, and the switch would turn off. And you could use that to turn on heat or to turn on air. Thermometers that had the mercury in there, is when the mercury would rise again, it would get hotter because it was expanding, and it would cause the switch to turn on or off. Geothermal systems, these are used in a lot of places because the temperature of the earth tends to stay well above freezing as you go deep down in. And so pipes are put into the ground, usually in U shapes, and they can shoot water in there. And then as the water gets some hot energy as you go further and further down into the crust, then it would send back up hot energy, a lot of times in the form of steam. Now, on your other note sheet, we're going to switch to the one that says temperature scales and talk quickly about the two common temperature scales, and they are Celsius and Kelvin. So Celsius is the common metric scale that we use in science and the scientific community. It's the standard form. Like I was saying before, water freezes at 0 degrees Celsius, water boils at 100 degrees Celsius. You'll look at a YouTube Eureka clip later that talks a little bit about the scientist Anders Celsius, who actually invented the scale and how he did so. Then there was another scientist, his name was Lord Kelvin, and he came up with a new temperature scale that was based off of Celsius. So it had the degree intervals were identical to the Celsius scale, but on a 273 point addition. So for example, water freezes at 0 degrees Celsius. Well, it freezes at 273 Kelvin. So you would just add 273 to that. Water boils at 100 Celsius. Well, it boils at 373 Kelvins. 100 plus 273. Why did Kelvin need to make this scale with such an odd thing? It's because of a theoretical temperature called absolute zero. So absolute zero is this theoretical temperature at which all molecules, all atoms, all particles in the world would just stop moving. So there would be no motion whatsoever. Even in solids, the particles are vibrating, but it would be so cold and so lacking in any energy that the particles would just be done. They wouldn't move anymore. Obviously, nothing living would survive this. Now, we've said here it's theoretical. We've never reached this temperature. We've gotten darn close. There's a special super duper scientific freezer somewhere in America where they got to about 200, I'm sorry, to about, I think 6 or 7 degrees Kelvin, so close to that zero, or negative 265, I want to say, degrees Celsius. So they've gotten very close to it, but they still can't seem to synthesize what it would be like to have absolutely any energy there. And that would be absolute zero. So that's why he came up with this temperature scale. Rather than saying absolute zero was negative 273 degrees Celsius, it was easier to say absolute zero is 0 kelvins, and that would be equal to negative 273 degrees Celsius. So guess what? You have to know how to convert between Celsius and kelvins. It's not that hard because you just add or subtract 273. So you can convert from Celsius to Kelvin by subtracting 273. So if I have, this is all stated kind of backwards here. You can convert to, so if I have kelvins, let's just take a look at this. If I have kelvins and I take away 273 degrees, I'm going to get my temperature in Celsius. If I have degrees Celsius and I add 273 degrees, then I can get my temperature in kelvins. I'm sorry that that's typed backwards. My mistake. So let's think about this. Water boils at 100 degrees Celsius. So if I plug in 100 degrees Celsius plus 273, I get my kelvins, 373. So let's try to convert to kelvins on your sheets. For the other example, 22 plus 273, and you should get 295 kelvins. You also need to know how to work this in reverse. So I'm going to leave you guys with some practice problems on working it in reverse, which would just, again, to be if I give it to you in kelvins, subtract 273 to find Celsius. And that is it. Make sure you glue those into the temperature on page 40 and the phase change on page 41.